Okay, this is a good problem to work on because it might be real difficult to analyze when you're looking at a DC and AC source for current or voltage. But we notice there's two ground symbols, and if you notice that each of these elements, besides these two are in series, so they can be combined to one element. Let's call these two elements together Z sub 1. Okay. And just for simplicity, I'll redraw this in a really small circuit. Let's see, this is X of L. Over here we have R sub 1. And then we have Z sub 1. Okay. That's the circuit. Z sub 1 is equal to R2 plus X of C. We don't know what X of C is yet. We don't know what X of L is yet. We wouldn't know them if we didn't have a frequency. If this was a DC source, this is an AC source, after a few seconds of running the circuit, the capacitor would be an open, the inductor would be a short. The resistive loads would still have some voltage drop across it and some current flowing through it. Although the R2 wouldn't have a current flowing through it because the capacitor would be an open, we would share the same voltage drop between here and here, which means there'd be no current flowing through R2 at that point. There would be current flowing through R1, and that would be pretty much it. But let's redraw this so that it's a lot more easier to understand. Okay, because notice this is the same point for all these elements. So let's just make that the top line. Okay, now from here I'm going to go down and make that source. All right, and our ground is right here. That's our next point. So I'm going to make that the bottom line. So what can I put in between that? Well, we have top to bottom on the inductor. And we have top to bottom on the resistor. And we have top to bottom on Z sub 1. And you notice all three of these sources are in parallel with I, with the current source. And above here you see that the product over sum is equal to multiplication over the addition of these values. So we have to figure out X of L first. That's 2 pi FL, and X of C is 1 over 2 pi F of C. These are the algebraic equations for the impedances for these values, and that's what we're going to need to do in order to solve for the, we want to find VS right here. We want to find the voltage across VL and the voltage across the capacitive load, V sub C. And I'll do that on the big board. Okay, so now we're going to solve this problem. And just to reiterate what we have here, I'm going to redraw our current source, which is 8 milliamps at an angle of 0 degrees. I equal to 8 milliamps at an angle of 0 degrees. Okay, and we have resistor or inductor. I'll just draw the regular symbols. And here we have a resistor And then here we have a resistor in series with a capacitor. So this is X of L. This is R1. This is R2. This is X of C. Okay. And so we all have them in parallel, and these two are in series. So, let's do. It doesn't really matter. We could do these in parallel first. So ZT is equal to X of L in parallel with R1 in parallel with a combination of R2 minus plus X of C, which is minus J, whatever the value is. So let's find what X of L is first and what X of C is first. And I will be using a scientific calculator to do these problems. So, let's see, 2 times pi times 10,000 and to multiply that by, we have two values. We have 47 millihenries, 0.047, and we have the capacitive value, which is 1 divided by parentheses 2 times pi times 10,000 times 0.01, and I should put that in parentheses too, times 0.01. Yes, a parenthesis. I have 1, I'll show it here on the calculator actually, 1 divided by parentheses 2 times pi times 10,000 times parentheses 0.01 times 10 to the power of -6, because that -6 represents micro. And I come over here to the end of the line here, hit menu, go to 2, number 1, and convert to decimal, and then I'm going to enter that. So I get 1592. So I'll write it here. We have X of L equal to 2 pi FL, which is equal to 2 times 3.14 times 10k hertz times 47 millihenries. That whole thing. This is all equal to 1592. 1,592 ohms at an angle of 90 degrees. Okay. And then we have X of C. 1 divided by 2 times pi times F times C. And that's equal to, and this is 2 times 3.14. I could just put 6.28. 10 kilohertz times 0.01 microfarads. And that's equal to that's actually equal to 1,592 ohms at an angle of -90 degrees. This inductive value is actually 2953. Okay, so now that we have all of our impedance values, now we can solve for the total impedance, because we didn't actually have the total, we didn't have these values in impedance, we just had the values of their I'm not sure what you would actually call that, the component value, the units, the component units, I guess you could say. The units for resistance is ohms, but the units for a capacitor is farads and units for an inductor is in henries. And so that's how we measure them. And if we have an inductor, and I'll probably show this on an actual practical circuit, because I could hook up an AC, I could use a function generator to create an AC waveform, or I could just use a transformer and do it the right way and use the outlet on the wall to do 120 volts. If I use a step down, if I step it down to 12 volts using rectification and all that, I could probably make a pretty useful voltage supply for DC or AC circuit analysis. However, I don't really need, well, not for rectification, but for DC analysis. But without rectification, we can do AC analysis. But it's easier to use a function generator because I can just supply how much voltages there is, so it's much more safer. And I can use an oscilloscope to measure the waveforms as well. Also, with the function generator, when I plug it power into the breadboard, and I have a circuit built with resistors, inductors, and capacitors, they act just like the inductive loads would at a real factory by theory, and the math works. So it's the same thing that happens in a building that's got an inductive load creating something, and you got some like computer here that's got some load that's always running, and then you have some capacitive load that's doing something, and another computer to make sure that capacitive load doesn't get high frequency because then the current goes up. So I'm not sure what kind of system that would be, but a lot of companies have capacitive loads and inductive loads and resistive loads. Our house, this light right now is a resistive load. So solving for this circuit though, let's get to it. We got X of L, let's say 2.9K, and then X of C, 1.59K. Let's do three significant figures, 2.95. Now R1, let's see, R1 is 4.7K. And then R2 is 1.8K. Well, let's do X of L in parallel with R1. So Z sub 1, I'll redraw the circuit so we can see what we're doing here. I'm going to redraw this circuit so I can combine these elements. And let's just say that it's going to be a square. And that's going to be Z of 1. All right. Then we come over here, and then we have, let's solve this series combination, Z sub 2. Okay. These two in parallel, and these two in series. So Z sub 1. Z sub 1 is equal to X of L in parallel with R1, which is equal to, I'm going to be really consistent with how I do that. So this is equal to R1 times X of L over R1 plus X of L. Okay. That's equal to let's see, R1 is 4,700K, 4.7K ohms. Yeah, so make very consistent at an angle of 0 degrees, and multiply that by X of L, which is 2.95K, at an angle of 90 degrees. And this is all going to be 4.7 plus J of 2.95K ohms. And I put the K ohms on the end so I don't have to keep putting K ohms in between here. I could do that, but it makes it much more efficient and concise. But I'm gonna store z sub 1. I'm gonna calculate z sub 1 and store it in the value a. So 4700 times the 2.9, 2953, that's going to be 1.38 times 1.39 times 10 to the 7th. Times 10 to the 7th, that's going to be ohm squared at an angle of 90 degrees. And then the square root of 4700 squared plus the 2953 squared. And I'm going to use the actual value squared, which is makes it 2954. Ohms at an angle of trig inverse tangent of the y value divided by 4700, 32.1 degrees. Now, since we're using the whole value with the resistor, let's take the 4700 squared plus 2950 squared, because that would have been 2.95 squared, and that we get oh no, that's not right. The degrees is, but I forgot the square to 4700 when I did this value, and that made it. You got to be very careful with these calculations. You got to make sure you do it right. 5551. At an angle of 32.1 degrees. All right. And I got 5549 if I just used 4700 and 2950. So that extra 3 brought it up 2 values. So that's pretty significant to me. Now I'm going to take that 1.38 value and divide that by that 5551. $2,500, $2,501. And the degrees, that'll be 57.9. That looks like an S. Here we go. All right, so now we have Z sub 1. That's right here. But now we need Z sub 2. And I'm going to do that over here. And make sure that you can see, yeah, you can see part of that. Okay. So Z sub 2 is equal to R2 plus X of C. But that's equal to making all this notation means is that it's the same from above. So this whole equation is consistent, and this means that it's just repeated above. So if you got some big equation like P average, for instance, I'm gonna keep writing that down. And wouldn't make sense. So R2 is 1800 K ohms, and we're gonna add that to J of negative 1.59 K ohms. Here's another way of writing it. This one I only use parentheses because of the negative value. We can rewrite this as 1.8 minus j of 1.59 k ohms. Or we can do the Pythagorean theorem. And before I do that, I'm going to store this value as A, and the degrees as B. Now, here we're going to do the Pythagorean theorem, 1800 squared plus the 1591, and I'm using the actual value, really 1591.55, but when I do that and square it, add it to the 1800 squared and take the square root of all that, 2403 is the 2403 ohms at an angle of, well, we could do the trig inverse of this and negative 159494.309 divided by 1800, negative 41.5. Alright, so now we got Z1 and Z2. Now these two are parallel. So it would be better to do the product over sum of these two. And since we got to do the product over sum of these two, the one we really only have to deal with solving is this one, because this one has this ratio change, and that'll change to x and y from what it looks like here. So we can't use any of these values. We have to take this and do the trig cosine, take this value and multiply by the cosine of this value in degrees, and the same thing with the sine. Then we add that to these two values. We don't even need this, really. This was just an extra step in case we needed it. So if we do that A, because that A represents in 2501, A times cosine of B, 1330. So Z sub t is going to be equal to this x value, which is 1330, plus this 1800 plus j of the x value, y value, A times the sine of B, 2117 minus 1591.92. And that's the Z sub t. Let's add those together. This is pretty easy. That's another 1,000, that makes 2,800, and then 1330, that makes 2130. Oh, making my numbers bad. And then this is going to be a positive j, and this value minus 1592 or 1591. So it's probably just subtract that from the actual value. So I got to go all the way up here for it because I didn't save it. So 526. All right, so let's do the square root of that. After I add 1800 to that value, there we go. Oh, that was actually 3130. Forgot, that's 2800, and then that, yeah. So square root of that value squared plus 526 squared, 3174. And then the inverse tangent of that 526 over the 3130, that's 9.54 degrees. All right, so V is going to be the same for X of L for VS, but it'll be different for X of C because we have a voltage divide between R2 and X of C. So 8 milliamps 25.4 degrees. So Z sub T, we have, I'm sorry, V source should be equal to I times Z sub T, which is equal to 8 milliamps and angle 0 degrees times 3174 ohms at an angle of 9.54 degrees. And that'll come to 25.4 volts at an angle of 9.54 degrees. And if we want to know X of C, we just look at Z sub 1. Well, we know the voltage across both of them, so we just do the voltage across X of C. So V X of C is equal to Vs X of C over Z sub 2. Z sub 2 represents that value, so we have this times X of C. X of C we have is 1592. And that's all over Z sub 2. And we already calculated Z sub 2 is 24 ohms. 3 ohms at an angle of negative 41.5 degrees. Now, if we do that, multiply that by 1592, and I'm just going to use regular numbers here, we get 16.8, and that is not right because that's not the back of the book said. Z sub T for some reason I did the math, I did the algebra right, but the math calculations was not right. The square root of 3130 squared plus 526, 3130. Oh. Alright, so let's just keep this recording and let's see what I did wrong. Z sub T is that they're in parallel. Okay, now now that we got everything calculated, now that we got everything calculated, now we can solve for the z sub t, the total impedance. Once we know the total impedance, we can solve for Vs, which is here. Okay, we also want to know what the voltage is here, and cross X of C, and the voltage cross X of L. Not really written right, but hopefully you can understand. This is voltage of X of L. This is voltage of X of C. Probably better if I use color markers next time. All right. So let's do the Z sub t. That's going to be equal to Z sub 1 and parallel with Z sub 2, which is equal to Z sub 1 times Z sub 2 over Z sub 1 plus Z sub 2. And we need to understand what Z sub 1 is first, because we got to calculate that. And I'm going to save, well, I have already saved this value as A on a calculator, and this value of degrees, this value of ohms in the calculator is A, and this value of degrees as B. So if I take A times the cosine of B, I get 1330 ohms. So I could rewrite this as Z sub t. That's equal to well, let's do the top first. The product of Z sub 1, 25.01 ohms at an angle of 57.9 degrees. Let's multiply that by Z sub 2, which is 24.03 ohms at an angle of negative 41.5 degrees. All right, and then here we've got 1330 plus the 1800 plus J of, well, let's do that at value A times the sine of B, 2117 minus 1592 from here. And that's all in ohms. So if we do this, we get Z sub t is equal to, let's see, 2501 times 2403. That's 6.01 times 10 to the 6th ohms squared at an angle of 57.9 plus a negative 41.5. Well, we're only 16.4 away. So let's get 16.4 degrees here, and we're going to divide that by 1330 plus 1800, 3130 plus J of 526, 525, and that's going to be equal to whatever this Pythagorean theorem is, that value. Let's do that first. 3130 squared plus 525 squared. We get 3174. Do it down here. Z sub t is equal to we got 3174 ohms at an angle of let's see, 525 divided by 3130. 9.52. So then this value, z sub t, is equal to that big value divided by 3174, 1894. That's a total impedance, 1,894 ohms thrown through this whole circuit. So I can redraw this as always good to go draw a ground first. Z T. Okay, so we want to know what Vs here is because we know this is I flowing through. This is I flowing through the circuit right here, and then this voltage drop across here is going to be the same across all of them. So except for this F to C. It'll be the same for X sub L, R1, and Z sub 2. And Z sub 1 since both of those are in parallel. The angle here would be 16.4 minus 9.52, which is 6.88 degrees. So we know what the angle, we know what the impedance is. Let's find the voltage. Let's multiply that 1894 times 8 milliamps. 15.1. So I is equal to V is equal to Vs is equal to the total current times Vs or Is times Zs source total. We just use a subscript to remember what it is we're looking at and calculating. But this is, I'll just write this out. 8 milliamps at an angle of 0 degrees times 1894, or I could say 1.89 k ohms. That way we're consistent with this because this has milliamps. Go 0.008. But I like to use 3 significant figures with things. And this is equal to 15.1 volts at an angle of 6.88 degrees. Here's your first answer. All that work, here's your first answer. Huh. There. Then the second answer, what's X of L? Well, X of L is also equal to 15.1 volts at an angle of 6.88 degrees. But if I want to solve, we want to solve for X of C, we have to use the voltage divider formula, and that's Vs times the voltage of X of C is equal to Vs times X of C divided by the total impedance here, which is Z sub 2. So V X of C, that's going to be equal to the source voltage, which is 15.1 volts at an angle of 6.88 degrees, times X of C. X of C, we calculated earlier, it's 1592 at an angle of negative 90 degrees. And we're going to divide that by Z sub 2. Z sub 2 is 2,403 ohms. And that's at an angle of negative 41.5 degrees. So even this step here, even to get X of C, we got to go a little bit further in calculations just to get that. So let's multiply it by 1592 and divide it by 2403. We get 10 volts. And the angle, we add these together, 6.88 minus 90, and then subtract that from a negative value, we add 41.5, and we get negative 41.6 degrees. And if I did that correctly. I'm pretty sure that's right. So this is the 3 answers you'll get for that problem. So remember, we redrew this from its original. It didn't look anything like this, but this is the way it's drawn, and it can be redrawn in a different way to make it look more cooler, make it look more complex, make it look more concise. But this is the algebra behind it to solve for that problem. It doesn't really take long. If you have a Python programming language or Java or something else that's equivalent, you could create the logic behind this to solve it for you. So if you're going to do this circuit all the time and you're going to use different values, you can create a program that'll calculate the values for you just by asking you what's x of c, what's x of l, what's R1, what's R2, and what's the total current source. And the degrees for those values would be a little more complex, but it would be there and it would do the math for you. So this is just the basic algebra behind it on dry erase board. You could do it on pencil, of course, but hope you like it.